All right, everybody. So what we're working on now are 3 practice problems on stoichiometry. So at this point, if you haven't done these problems and you're just going to walk through them with me now, that's great. If you have done them, you can use this to check your answers and just kind of scooch forward to the end of the problem. So let's take a look. There are 3 of these, and here we go. First question says, when silicon dioxide, and for the record, as I go through, I'm just going to underline parts that I think will be important. When silicon dioxide is heated with pure carbon, silicon monocarbide and carbon monoxide gas are produced. How many grams of carbon monoxide gas are produced when you start with 50 grams of silicon dioxide? Oakley dokley. Extra challenge, single T-chart line format, which is my personal favorite because it makes my little nerd heart go pitter-pat. So remember that every stoichiometry problem has to start with a balanced equation. So here we go. Using the things that I underlined in the first sentence. Silicon dioxide, Si, dioxide is going to be O2. Heated with pure carbon, let's just see, it is not genuine, so we just draw a C. We get silicon monocarbide, so that's just SiC, and carbon monoxide gas are produced. Remember that beyond writing it, I also have to balance it. So if I have 2 oxygens on this side, I'm going to need a 2 there to balance out my oxygens. My silicons are balanced as written. I have 1 carbon here and 1, 2, 3 carbons over here, which means I need 3 right there. So this is my balanced equation. So I'm starting, now going into the second sentence, with 50 grams of silicon dioxide, and I want to get to grams of carbon monoxide gas. So I'm going from here to here. So I've done the first step, which is write out a balanced equation. Now I'm going to try to do this all in one line. Remember, step 2 of stoichiometry is mass to mole. Here I start with 50.0 grams. It's important for sig figs of SiO2. Mass to mole. So here we go. We're going to find the molar mass of silicon dioxide. So let me add that up for you as we speak. 1 silicon, 2 oxygens has a molar mass of 60.09 grams is equal to 1 mole SiO2. Now remember, I'm really going to keep track of my moles here. I'm not just going to say 1 mole. I'm going to say 1 mole of SiO2. That's going to be important to keep track of because there are going to be lots of moles floating around this problem. 1 mole of SiO2. Okay, step 3 is using a mole-to-mole conversion. Think about that mole-hole converter. Using a mole-to-mole conversion with my balanced equation. I know that for every 1 mole of silicon dioxide, I actually get 2 moles of carbon monoxide. So I'm going to use that. 1 mole of SiO2 reacts to form 2 moles carbon monoxide. And then the very last part of the question is I want to get to grams of carbon monoxide. So I'm going to do 1 more. Now I'm converting moles into grams. So hopping on my trusty little TI, the molar mass of carbon monoxide is 28 grams, 28.01 grams. So here's what I like about what I've written. All of my units cancel out on the diagonals, just how I like. I have grams here, grams there, moles SiO2, moles SiO2, mole CO, mole CO. So the only thing I'm left with is grams of carbon monoxide, which is what I want. So plugging that through my T-chart, I'm going to do 50 times 2 times 28.1. Get my answer of 2,810 divided by 60.09. My calculator is going to spit out 46.763188 grams. How many sig figs can I keep? If I look at all the numbers, remember my mole numbers here do not contribute to my sig fig. So I'm looking at 50.0, 60.09, and 28.01. Looks like 50.0 has the fewest number of sig figs with 3, which means I can have 46.8 grams of carbon monoxide. All right, 1 up, next one. There we go. When yeast is added to a solution of glucose sugar, there's glucose, C6H12O6, the glucose is said to undergo fermentation and produce alcohol. Yay, when you're 21! This is how grapes are turned into wine. Given the unbalanced reaction below, calculate the mass of glucose. Again, I'm pulling out the things that I think are important. The mass of glucose needed at the beginning if I'd like to end up with 67.5 grams of ethanol. Okay, so let's take a look. Here's my equation down here. Now notice I said it wasn't balanced, which means I'm going to have to do a little thinking. So what I see here is I'm going to start with my hydrogens. I have 12 hydrogens here. 1, 2, 3, 4, 5, 6 hydrogens there. So my first easiest thing is I'm going to bloop, put a 2 right in front of the ethanol. So now my hydrogens are fixed. Now that I'm looking, I have 6 carbons here. 1, 2, 3, 4. Oh, I might need some more. Carbons. I'm going to put a 2 there. I chose to put a 2 in front of the carbon dioxide because I don't want to mess with my hydrogens if I don't have to. Those are nice and clean and balanced. So now 6 carbons over here. 1, 2, 3, 4 in here. 2 times 2. 5, 6. My carbons are good. Let's check my oxygens. 6 on one side. 1, 2 here, and then 4 here. 2 plus 4 is 6, so I am balanced. Okay, setting it up in this nice big long line. Like I said, if you can like quietly in your nerd heart kind of secretly enjoy these, and if you don't yet, you just might. They're nerdy fun. So we start with 67.5 grams of ethanol. So like with all T-chart problems, the number given in the problem goes in the upper left. I'm going to abbreviate ethanol. 67.5 grams of ethanol. So first step in my mole process, I've balanced my chemical equation. I'm next going to do second part, grams into moles. Grams of ethanol into moles of ethanol. I need to find the molar mass of this, C2H5OH. So I'm going to take my 2 carbons, add that. I have 6 hydrogens, even though they're split. That is a convention of organic chemistry. It's the little OH here at the end that makes it a alcohol. So plus, which gives me a molar mass of 46.07 grams, is 1 mole of ethanol. Again, notice I'm keeping track of what moles of what. And again, remember, it's a quarter point off for every number in your T-chart that is without a unit. So if you fell out of those habits, get back in those habits. So my second part is my mole-hole converter. I'm going from moles of one thing into moles of something else using this balanced equation. I'm in ethanol. Where do I want to go? I'm reading back in my problem. I want to find glucose. Well, here that is over here. I know that for every 2 moles of ethanol, I get 1 mole of glucose. So for every 2 moles of ethanol, it went all wonky on me. Hang on. For every 2 moles of ethanol in my problem, I get 1 mole of glucose. And even if you just label it by like putting a G with them or something like that, you just need to make sure you have a little label there. Okay, my last problem bit, moles into mass. I want to find the mass of glucose. One last part of my T-chart, moles of glucose. Now my molar mass, I have 6 carbons, 12 hydrogens. I'm calculating this live as we speak. Maybe I should have done this before. Oh well. That's 16 times 6. 180.156 grams. All right, and then you know the drill. Everything you multiply across. So 67.5 times 1 times 1 times 180.156. I get a big number. I divide it by 46.07 and then divide it by 2. And my answer is 131. Again, I'm going to write down what my calculator spits out because it's good practice for sig figs. Big number. Okay, I'm looking at my numbers. These are the numbers that I'm going to look at to determine how many sig figs I have. It looks like I can keep 3, so my answer will be 132. grams. All right, last one. Here we go. Acetylene gas, C2H2, is used in welders' torches because of the large amount of heat produced. Okay, I bet that's going to be important. Acetylene gas reacts with oxygen in a classic combustion reaction. Ooh, look in your chemical reaction notes to remember what those products are. How many grams of oxygen are needed for the complete combustion of 150 grams of acetylene? Okay, so the first thing, remember, first step is always write the balanced chemical reaction. So C2H2, I know it reacts with oxygen. I'm going to remember my genuine. And then it says this is a classic combustion reaction. Now, if you remember back to first semester, combustion always results in two things, CO2 and H2O. So now I need to balance it. The first thing that I see is I have 2 carbons over here and 1 carbon over here. So my easiest, quickest fix is to put a 2 in the front, just like that. I have 2 hydrogens here, 2 hydrogens over here. This is going well. I have 2 oxygens here, and then 1, 2 times 2, this is 4 oxygens, 5. Okay, this is when it gets exciting. If I have 5, I'm going to try then bumping everything up by a factor. So I'm going to take away my 2 and instead go for 4 and double that. And again, this kind of give and take is very much, remember, this is very much how balancing goes. Is you try one thing, fixes the carbons, but let's see what else it does. Now I have 2 times 2, I have 4 hydrogens here. I'm going to want to put a 2 there. Let's check my oxygens. 4 times 2, 8, plus 2 is 10 oxygens. So I'm going to put a 5 right there. 5 times 2 gives me 10. Now I want to know how many grams of oxygen are needed when I start with 150 grams of acetylene gas. So 150 grams C2H2, and set up your long, nerdy T-chart. Woo! Okay, so first thing is I need the molar mass, 12.01. I have 2 of those and then 2 hydrogens. And I get a molar mass of 26.036 grams, and that's 1 mole of C2H2. Now I go to my balanced equation. So I'm starting here, and this time I want to go here. So I know that for every, again, I'm looking at these numbers. I know that for every 2 moles of C2H2, I get 5 moles of oxygen. And then lastly, the question is asking for grams of oxygen. So I'm going to do that final step of converting my moles of oxygen into grams. And once we're there, you know the drill, multiply it all out. 150 times 5 times 32 divided by 26.036 divided by 2. And again, I'm going to write down what my calculator spits out and then think about sig figs. So 460.9000. With sig figs, let's see here. I have 32, 26.061, and 150. Looks like the fewest number of sig figs I have in this case is 2. So I'm going to write this as 460 grams. Notice the answer isn't 46. I still need to show how big the number is, but I can tack zeros onto the end without changing the number of sig figs. All right, so these are 3 stoichiometry practice problems.